In this work, we proposed a new trajectory optimization method for legged robots, stage contact optimization, or SCO. SCO combines aspects of contact-implicit optimization and multi-phase hybrid trajectory optimization to solve two main goals. One, allow the contact sequence to vary so that SCO can find results without a predefined contact sequence. And two, provide a full order optimization result for a given system and desired behavior. We want to use trajectory optimization on legged robots to determine optimal behaviors, which can be used in many applications, notably platform execution or robot model studies. However, this problem becomes much more complex due to inherent non-smooth impact dynamics required for locomotion. Hybrid trajectory optimization, or HTO, is a common form of solving these types of problems, which links together continuous phases with discrete reset events to handle impacts. For HTO, the user is required to define the contact sequence, which restrains the feasible trajectories. However, poor contact sequences lead to suboptimal results. As the problem complexity increases, iterative methods are often needed to determine the most optimal contact sequence. Contact-Implicit Optimization, or CIO, allows the optimizer to choose a contact sequence during the optimization through a set of complementarity constraints. The user no longer defines the contact sequence, but this adds significant complexity, making it very difficult to solve. Many previous works have focused on improvements to CIO. These various attempts all have unique benefits, decreasing overall solve times, increasing convergence rates. However, the final outputs are still subject to CIO struggles with full order models. In this work, we sought to combine these strategies as well as taking advantage of HTO's convergence properties in one algorithm. SCO combines CIO and HTO in one algorithm. The user supplies desired start, end conditions, and cost function, and then receives a full order solution. SCO starts with a staged sinusoidal CIO solve. The contact sequence is then extracted from this result to set up a HTO problem, which is seeded with a calculated full robot state at each time step. Finally, the HTO problem is solved and the user receives our full order trajectory. For simple cases, the user can intuitively determine the optimal contact sequence, but what if we add more complexity? For crossing this pit, how many steps do we need to take before jumping? Do we jump off of both legs or just one? How many steps are needed to reach the end goal? Here we can see how SCO handles the problem in stages and ultimately outputs a quality trajectory to cross the gap. Stage 1 finds a good contact sequence, and then a seed is computed to fill in the missing full order data. Stage 2 then optimizes this full order dynamic model and creates a smooth result. In this example, compared to CIO, HCIO, and HTO, SCO is able to solve the problem almost as optimally as HCO's cost, while being an order of magnitude faster. When comparing the SCO and HCIO results directly, we said that HTO had many short context switches to come in its results, showing CIO's tendency to fall subject to brittle output trajectories. SCO managed this problem more elegantly with nearly the same cost, but again, not even to mention this execution time difference. Notably, SCO was even faster than HTO due to a seeding in stage 2 optimization with this quality seed. This was the case even when running HTO with SCO's found contact sequence. However, what happens if we extend SCO to attempt trajectory optimization on a complex 18 degree of freedom spatial quadruped? SCO achieves a cost in the range of the HTO results and also in a comparable time to these HTO solves. However, once again, these HTO results were found through many gate studies, and for even more complicated scenarios, many hours could be spent trying to find the best contact sequence. Also, SCO managed to beat out HTO's cost with the flying trot gate, which is a very commonly used all-purpose quadruped gate. We also note that CIO failed to converge for this problem despite applying all of our tricks using staging and seeding. HCIO also achieves a notable result by beating out the HTO flying trot, but took almost 20 hours to converge. In conclusion, SCO successfully combines HTO's speed and convergence properties and CIO's ability to automatically determine the contact sequence. SCO results show promise in complex 2D and 3D applications and could be beneficial in robot platform execution or modeling studies. Future work could look into validation of SCO results on platform, implementation of faster NLP solvers, as well as further work on tuning SCO's included parameters.